In this unit, we are going to continue our discussions on network security. It's a pretty big topic. We had 2 units in CT395. We also have 2 units in CT420 that discuss network security. So let's get started. I'm going to cover 3 topics in this unit. In this video, I'm going to talk about protocols and attacks. In the second video, I discuss secure configurations. And then finally, virtualization in the cloud, which is an emerging topic. So protocols and attacks, our idea here with protocols and attacks, I want to describe some common protocols that are used in networking and some specific attacks that are used on those protocols. I want to preface this discussion by mentioning that a lot of these attacks that I'll discuss, some of them are rather old. They've been around for a long time. And I mentioned this before, I think in the other courses I mentioned this too, that there are lots of types of attacks that can happen, and the possibilities are endless, and we can't sit here and describe every recent attack that's happened. I've had a lot of students who will contact me and say, you know, Brian, there was this attack last week that the attacker, and they'll go on to describe some specific way that they found some vulnerability in a protocol and whatnot. And that's our goal here in these courses, is not to describe every possible attack, but rather to describe some of the attacks that have happened in the past so that we can understand how attackers think and how and not even so much how they think, but how there's so many little vulnerabilities that if someone can find that chink in the armor, they can get through any system. And it's important to understand and try to think critically about all the different ways that attackers could, when we're looking at how things work, we want to try to think like an attacker and think, okay, how could somebody take advantage of this protocol? How could somebody use this information that's exposed through this protocol against me? And to try to think about ways to mitigate those attacks. And like I said, we can't possibly think of everything or talk about every possible attack, but we want to use some of the classic cases here that are easy to understand how it happened, to use those as examples that we can use going forward. So let's talk about some of these protocols. So what is a protocol? It's rules of conduct and communication. That's the Webster's Dictionary definition of a protocol, essential for proper communication between network devices. So just like we have protocols in a classroom, right? So when we sit around a classroom, there are certain protocols that we follow. If the instructor is lecturing and you have a question, you don't just blurt out the question. In most cases, you put your hand up to indicate that you have a question to ask, and then at the next break, when the professor has a second, they'll call on you to ask your question. They'll answer the question, and so forth. So there's a certain set of protocols that we all sort of comply with. Some of those protocols are codified in some kind of rules. And some of those protocols are just accepted agreements between parties because that's just the way it's been, for example. And we have the same kinds of protocols in computing. Some protocols are defined through RFCs and IEEE standards and so forth. And some protocols emerge just through standardization of the way we do certain things. A lot of APIs and things like that just sort of emerge because of best practices. So the Transmission Control Protocol, Internet Protocol, or TCP IP suite is one of the most common protocols that we use for the Internet and for local area networks. It's obviously one of the most common. I've talked about TCP IP more times than I can count in this class, the previous class, and all the other classes that I teach. We always bring it up. You guys are probably sick of seeing the OSI model over and over again, and probably sick of me telling you that the OSI model is sort of outdated, and the reality is the TCP model. But in any event, the TCP IP uses 4-layer architecture: the network interface, internet transport, application. So we always talk about the OSI model being 7 layers, and the TCP IP model is 5 layers. Really, the network interface layer is 2 separate layers in TCP IP, but they're very closely related. Mostly because the standards usually define both layer 1 and layer 2 protocols or communications and things like that at both of those layers. But in any event, I've showed you this model before. We've talked about it many times. I don't want to spend too much time talking about it, so let's dive into some of these protocols that we use with TCP IP. One is the Internet Control Message Protocol, and this sort of sits outside of TCP IP. It uses IP, right? So it uses the IP protocol. But it does not rely on TCP or UDP, which is the other part of the suite. It is only IP. Basically, it's used by devices to communicate updates or send information to other devices. So this is how things like routers and switches communicate with one another, and how we do some troubleshooting on our networks. They're basically divided into 2 classes, these ICMP messages. You have informational and query messages, and then error messages. So ICMP usually have a type which identifies a general message category, the code, which is additional information about the type, the checksum, which verifies the integrity, although it doesn't meet the standards that we have in IT security for verifying integrity, but it's certainly one check, and then the message body. And these are the different types. So, for example, 0, destination network unreachable, destination host unreachable, destination protocol unreachable, and so forth and so on. Some of these look familiar to you, I'm sure. And some of you might be thinking, oh yeah, I know what these are. I see these when I try to do a ping. If I do a ping and I get an error message or something, it might give you one of these error codes. But instead of seeing the code, you'll see the actual text there, or some variation of that text based on how whatever library that you're using to with that command might interpret the message or the description a little bit different. But we've seen these before. So some of the tools that you've probably used are things like ping. It relies on ICMP, path ping, trace route, and so forth. So there's a whole suite of tools that we can use to utilize ICMP. So just like we can use ICMP for troubleshooting and to figure out certain things about how our network works, our attackers can do the same thing. So that's the first vulnerability that ICMP brings to us is the same information that we can use to our advantage, our attackers can use against us. So network discovery is certainly one thing. Smurf attack is a common attack. Well, it used to be a very common attack. Basically, a Smurf attack is where you send ICMP. So an ICMP message, when you send it, you have your return address so that the person can get back to you, right? So if you're trying to query a network device, right, I'm pinging a device and I'm expecting to get a response back from that device. Well, what if I flood the network with ICMP requests to all these different devices on the network? Maybe I've got thousands of devices on my network and I send ICMP requests to all of those for a query. But for the response, I indicate one workstation for the response. Well, all of a sudden, that workstation is going to get inundated with all of these responses that it didn't even request and it doesn't know what to do with. And that's a form of a denial of service attack, which can be done with ICMP. So you have an ICMP redirect attack, which works very similar to a Smurf attack. It's the same idea. And then the ping of death, which was a common thing with old versions of Windows, although I think most operating systems today are basically impervious to this, but there's a certain format, it's a protocol. There's rules that you have to follow in these packets that you create for ICMP. And if you malform a packet, if you create a packet that is that's incorrect, for example, then some systems won't know what to do with it and they crash. And that's what the ping of death was. It used to be with Windows, you could send a ping with a certain malformed ping to Windows. I think it was Windows 98, and it would cause a blue screen of death. You'd just be sitting there using your computer, and all of a sudden you get a blue screen of death because somebody sent you the ping of death. Obviously, a lot of these issues have been fixed, but that's not to say that there's some new vulnerability that might come out where somebody can't handle certain types of ping. And one of the things I want to mention here is that a lot of these computing platforms that we use every day, like that are based on well-established and well-known operating systems, I think we don't have to worry so much about this. But where I see this being an issue is when we're using alternative devices like SCADA and things like that, with like building controls, anything that has an operating system that uses TCP/IP for its transport mechanism, but it's not a real computer; it's a device. For example, you might have a thermostat in your house that connects to your Wi-Fi. Whether or not those devices have these vulnerabilities, I don't know. And I think there's a better chance for these vulnerabilities to exist in those devices because they're using a very lightweight operating system. In many cases, it's based on Linux, and it should be relatively impervious to these types of attacks. But certainly it's something that we could test for and that we could take a look at. So the next protocol is Simple Network Management Protocol, which does rely on TCP/IP. The basic concept behind SNMP is that most of our network equipment supports it in order for us to get information to and from those network devices over the network. So it's sort of a standardized way to read configuration data from our devices, to set data on our devices. There are ways that you can send updates to devices so that it works a little bit differently and so forth. All just basic network administration stuff that you've probably learned about SNMP in your router classes, and so your Windows classes will talk about it for sure. So every SNMP managed device will have an agent or some kind of service that listens for these SNMP commands and then carries out whatever the instructions are, whether it's a query for information or an update, for example. So the main vulnerability, I probably don't have to mention this, but one of the main vulnerabilities is that we can get information from SNMP, which is obviously something our attacker is going to look for, right? If they're doing reconnaissance, SNMP is one of the tools that they're going to have to try to get information. And most people say, well, gee, why don't I just protect those devices and have and the way you protect those devices, they have a password called a community string in older versions, especially of SNMP. By default, that community string was something very basic. It was like password, or I can't even remember, but in older devices, it defaulted to something that everyone knew. So if somebody bought a network device and didn't know any better and just plugged it in and started using it, they wouldn't realize that anybody could walk into their network and read configuration data from that device. There are some other vulnerabilities that were present in versions 1 and 2 of SNMP, but in version 3, which came out in 1998, they've improved a lot of the functionality. So SNMP was basically unworkable from an IT security standpoint prior to version 3. Though with version 3, it does give us some a little bit more protection. One of the main protections is now you have to have a username and a password along with encryption for SNMP version 3. It allows us to use encryption and usernames and passwords, which is much better than just that generic community string with no encryption at all. So certainly an improvement for sure. So we want to make sure, the takeaway here with SNMP is to make sure that you do not have any devices using version 1 or 2 of SNMP. If it is, you want to make sure it's disabled. You want to make sure that there's a community string, if you are using it, that's sufficiently complicated enough that an attacker wouldn't be able to brute force it very quickly. And if possible, use version 3 if it's available on all of your devices. The domain name system is another suite of protocols. Obviously, we all know what domain name system is used for. We talked about it before. It maps a symbolic name with its corresponding IP address. For example, when you type google.com, it might go and look up the IP address and find something like 172.217.6.206. Of course, Google has many different IP addresses. Every time you do a query for google.com, you're likely to get a different IP address. They have a high number of IP addresses. But in any event, it's sort of like our phone book of the internet. And one of the problems with DNS is, well, I guess one of the advantages and the problems with DNS is that it's decentralized. You have lots of different servers that host DNS, and they're all kind of in charge of themselves and getting updates on their own and updating other people and things like that. They just kind of update each other. It's a very loosely federated environment with DNS. So there is no single server, which is great. That gives us a very robust architecture from the perspective that failure is unlikely, because you've got all of these different managed devices all over the internet that can all do this independently. So if my DNS server fails, I'm not really going to affect the entire internet if that happens, because there are other DNS servers that are running. So again, it's that sort of distributed database that's great. The problem with distributed databases is that they're very susceptible to being poisoned, because who do you trust? It all comes down to trust. And with the DNS system, if I'm a DNS server, I have to trust somebody else who's going to give me updates about other DNS servers. And there are certain root DNS servers to which we can go to that if there's some vulnerability and trust between the root DNS servers. So and basically, and I'll talk about some of the attacks in a second, but just so you can see, this is an image of how DNS updates work. This is from your textbook, so you can certainly crack open the textbook to take a look at that, but I don't want to go through that whole diagram. The real takeaway here is to understand the distributed nature of DNS. So DNS can be the focus of attacks, and one of the common ones is DNS poisoning, which is substituting fraudulent IP addresses for the real IP address. So it can be done in a local host table, which I'm going to ask you to do in the labs. So in the labs, I have you go in and change your host table and try this, so you can see how easy it is to poison DNS on your local machine. Obviously, poisoning DNS with an actual DNS server, an external DNS server, is a bit more complicated, but it's not impossible. And if you have a DNS server running in your network and it's not running the latest versions of DNS, or it's not patched against some of these vulnerabilities, then you may have these vulnerabilities. They may exist just within your network, which means an attacker could poison DNS just within your network. Poisoning DNS does occur on the wider internet. It is possible, and it does periodically happen. You may have heard about some of the downtime with companies like Dying DNS not too long ago. Had some they're a major DNS provider on the internet, and they were the victim of a DNS poisoning attack. They were also the victim of a denial of service attack. And the reality is that DNS is sort of the Achilles heel of the internet, because all of the other technologies that we have are great, but if you don't know how to get the IP address of a node and you only have their name, all the technology in the world isn't going to help you if you can't get their name. So if you can compromise DNS, you can compromise almost all other communication on the internet, because most of us don't remember IP addresses. If I ask you to go to google.com using the IP address right now, I'm sure most of you don't remember that IP address that I showed you earlier in the slide deck. But if I told you to go to google.com, obviously you just go to google.com and it's easy. So we really rely heavily on DNS. So any vulnerabilities in DNS can certainly cause major issues on the internet. Even VPNs and things like that go down if we're using FQDNs and so forth. So one of the ways that attackers use DNS against us is zone transfer attacks. If you're using something like Active Directory, you could use zone transfer attack to get information about your entire network with a zone transfer. So Active Directory uses basically the protocols baked into DNS to store all this information about your network that's ripe for the picking from our attackers by simply asking for it in the DNS server. So you certainly want to make sure that you're using versions of Active Directory that are protected against these types of attacks, and that you're keeping that infrastructure patched and on the latest versions. There are two file transfer protocols that your book talks about, and I don't know why they only talk about two. There are many more than two, but the book only talks about file transfer protocol as an example of an insecure file transfer protocol, and they talk about secure transfer protocol as an example, which is their example of a secure file transfer protocol. There are other secure file transfer protocols, and there are other not secure file transfer protocols other than FTP. And you can certainly see lots of different examples of these in other textbooks, but your book only talks about these two. So when they talk about file transfer, they say it's unsecure TCP/IP protocol for transferring files. And the reason that it's unsecure, and again, it works very similar to HTTP, but the reason it's unsecure is it does not use encryption by default. FTP does not, unless your files are encrypted themselves, which you certainly could do. You could do file level encryption. And provide a key to your user or something like that. But the transfer of the data is not encrypted, unlike other protocols. The trivial file transfer protocol is very similar to FTP, but it's a very lightweight version. You may have used this if you've done any configuration changes on a router, a switch, or a firewall, and you use TFTP to transfer firmware updates and configuration files and so forth. Typically, TFTP doesn't even have username and password protection. FTP does have username and password protection as part of the protocol, but again, it's not secure. It's all in plain text. So there are different methods of using FTP. You can use it from the command line, from a web browser. Most of the major web browsers support FTP natively. And you can also download an FTP client, such as this one. This is FileZilla, which I showed you in one of the videos that I have for the lab. Some of you are curious how to use FTP to transfer files to and from your Linux machine, and FileZilla is a free application to Windows. There's one for Mac as well, and Linux. There's one for all three that you can use with to use FTP. One of the things about FTP that it survived for so long, even though it's not a secure protocol, is that FTP is very convenient. It's supported in everything. If you've got a command line on just about any system, it's very likely that you can FTP directly from that command line. So it works everywhere. You can very easily download a client for FTP. FileZilla is not a very large download. It's available everywhere. It works from the browser. So from most of the major web browsers, Firefox, Chrome, Internet Explorer, Safari, Opera, you name it, they all pretty much support FTP natively in the browser. So it's everywhere. So while it is insecure, it's extremely convenient. And it's appropriate to use FTP anywhere where you're not concerned about the security of the files themselves or with the usernames and passwords. So it's great for just, downloading files. And it's a little better than HTTP because of the management of downloading those files. There's a little bit, there's a few more features in FTP available from the client to manage, interrupted downloads and things like that, especially for larger files. So it's definitely still a big need for FTP, but it's important to understand that there are some vulnerabilities. For example, it does not use encryption. So everything that you transfer, your username and password is in plain text. anything that you're transferring is in plain text. And of course, it's vulnerable to a man-in-the-middle attack because there is no encryption. There's no mechanism to protect from that. So there is the secure file transfer protocol as well as file transfer protocol secure. There's two different versions. There's FTPS and SFTP, but both of them incorporate encryption. So you'll find that there is encryption. So FTPS, which uses SSL or TLS, and then there's SFTP, which uses a single TCP port and encrypts and compresses all data and the commands. I would say that SFTP is definitely the more common, but FTPS is also another protocol. They are not the same, so don't think that these are the same protocol. They are very different. You can't use FTPS to connect to an SFTP server, and likewise, you can't use an SFTP client to connect to an FTPS server. So something like FileZilla supports SFTP, but I don't believe they support FTPS. And I'm pretty sure that SFTP is the more common of these two protocols. So if you are going to expose data that you need to have encrypted and you don't, and they're using real usernames and passwords that you don't want to be compromised, then SFTP would be a much better choice. The other option is Secure Copy Protocol, or SCP, and this is a service that's usually part of Linux or Unix, and that's really where SCP kind of got its start, is in the Unix and Linux world, which, by the way, a Mac also natively supports SCP as a client, although I don't believe they have the server by default, but I suppose you could probably put it on there if it's like any other Unix machine. But it encrypts both files and commands, so file transfer cannot be interrupted or resumed, which is a problem, but hopefully to today's modern networks, it's not a big deal. It's found mainly on Linux and Unix platforms, as I said. It's not common in the Windows platform, in the Windows world, but you can get a free client for SCP. For example, in the labs, I ask you guys to download PuTTY to SSH into your Linux machines, whether it's Dunix 1 or your own Linux machine, and that does support SCP, so you can use SCP with PuTTY. So there are certainly ways to do it from Windows as well. But this is one reason that SCP is not as common as FTP and SFTP, because it is native to the Linux and Linux world, and probably 99% of business computing on the client side is done with Windows today. Although that's changing with things like Android, but for the most part, most of us deal with Windows in the organizational and corporate world. So some storage protocols. So when we talk about storage protocols, in many modern data centers, we have centralized storage that we share amongst the entire enterprise. So we have this enterprise data storage platform. It centralizes data storage. There's a lot of good IT security reasons to have centralized storage. We can control how backups work. We can make sure we're not going to lose data. We have control of that data. So lots of good reasons to do that. And usually that enterprise storage utilizes storage area networks, or SANs. You may have heard the term NAS, which is a little bit different. A lot of times a NAS is sitting on front of a SAN. So a NAS is where you have some operating system that controls the file system and exposes files using some file sharing protocol like SMB, or using UNC paths and things like that, or even network file system like NFS. But a SAN is quite literally a storage device that utilizes the network as transport for that storage device. So SANs can consolidate different storage facilities that appear as a single pool of locally attached devices. So when you're using a SAN, the SAN will look like a local drive on your computer. So it'll appear as a local drive. So some of the common protocols that are used for SANs, the first one is iSCSI. Some of you may remember in the old days we had a standard called SCSI, which you had these long ribbon cables. You could attach up to 7 devices to each ribbon cable and up to 14 devices per controller. It was certainly an enterprise type of technology. Most people didn't have this at home, for example, but iSCSI was utilized, SCSI was utilized for enterprise storage devices. Basically, iSCSI is the Ethernet version of SCSI, so it uses Ethernet to mount as SCSI, and this has become sort of the de facto standard for storage area networks using iSCSI. iSCSI, one of the challenges with iSCSI is the fact that it uses Ethernet, and Ethernet is a limited technology. So one of the other technologies that is really used is fiber channel. So fiber channel is much faster than Ethernet. You can see here it's up to 16 gigabits per second, and that's significantly faster than we routinely see with Ethernet. But in any event, Fiber channel is the other option. Then you have fiber channel over Ethernet, which encapsulates fiber channel frames over Ethernet networks, so it can use faster Ethernet networks while preserving the fiber channel protocol. And typically you would do that with fiber. So you have a fiber network using the Ethernet protocol through which you're using the fiber channel. So it's just a way to utilize those existing protocols and leverage those existing protocols. Fiber channel is wholly proprietary. I don't want to say proprietary, but it's it's not TCP/IP. There's no IP addresses or anything like that. Where fiber channel over Ethernet, you do have IP addresses. It's just using that fiber channel over the Ethernet protocol, because we're just utilizing the protocol that we already have available to us. Like I said, iSCSI, in my experience, is probably one of the more common because it's very easy to set up. It can use existing infrastructure. It can use your existing networking infrastructure. One thing that I would caution you about iSCSI is it's very easy to use iSCSI with your existing Ethernet infrastructure and not segregate it. And there's a variety of reasons that it's a good idea to keep storage area networks completely segregated, and I don't want to say air-gapped, but completely separated from all of your other networking. And one of them is performance reasons, because as you can imagine, these storage area networks use a tremendous amount of bandwidth on the devices to which they interconnect. And there's also some security reasons with things like encryption and so forth, where iSCSI is not as robust as many of the other protocols that we use on a LAN. So one of the strategies that IT security and IT administrators will use is having switches and network infrastructure completely dedicated to storage area networks. So all of the storage resides on a single network. So let's say I had a server that is both providing services to client machines and it's utilizing a SAN for its storage. I would have at least two Ethernet ports, at least two NICs on that machine. One port would connect to whatever switch is connected to my wider network, and the other one is connected directly to my storage area network. And we treat it as a completely isolated and separate infrastructure, the storage area networks. And there are a lot of different techniques that you have to use with iSCSI that maybe are a little outside the box with normal Ethernet, that you don't want to have to worry about those settings on your standard network. You don't need them, and they may break other things on that network. So for sure we want to keep that isolated, the storage area networks. Windows has a technology called NetBIOS. I'm sure many of you have heard of this, but NetBIOS is basically what allows you to type in a host name in a Windows machine without DNS running on your network, for example, and being able to find other machines on the network. Microsoft developed this for small businesses and home users who don't have the resources to install a domain controller or something like that to manage communication between all these different devices. But there's a small enough network that a peer-to-peer relationship works fine. And normally in IT, we usually talk about how peer-to-peer networking is only really effective with up to 10 computers, and after that you really need to step up to something where you have some centralized control over those services. It runs over TCP/IP, so it does use TCP/IP. Each computer in the network has both an IP address and a NetBIOS name, but there are various attacks. For example, attackers can use computer names, the contents of a remote name cache including IP addresses. They can get a list of local NetBIOS names by simply running, the query on their machine for NetBIOS. You can go out and list all of the machines that are nearby with NetBIOS. Even if you're not using NetBIOS on your network, it's enabled on most Windows machines, which means if I'm an attacker and I jack into your network, I can start looking for machines using NetBIOS. And I can start identifying host names, and from that I can start doing more reconnaissance. So it's sort of a good starting point for a network attack. So it's good to be aware that it exists and that we may need to lock down NetBIOS or somehow deal with NetBIOS. Another tool, Telnet, is a protocol that's used for, it's an older protocol that's used for text-based communication over TCP/IP. Basically, it allowed terminal emulation, so you can, it's sort of like SSH. When we use SSH to connect to our Linux machines, that works very similar to Telnet, only SSH is encrypted, where Telnet is not encrypted. So the reason that I like to mention Telnet, well, first of all, the security vulnerability is if you log into a machine with Telnet, nothing is encrypted, just like FTP. It's all completely unencrypted. But the reason I like to talk about Telnet and IT security is Telnet is a great tool for attackers, because you can open up a command line and you can start telnetting to ports, and you can start seeing what those ports are doing on other machines. Now, there are automated tools to do that as well, like Nmap and so forth. I don't think we use Nmap. Well, we do have one lab where we talk about Nmap, and you can install a GUI-based version of Nmap. But But there are lots of tools that you can use for network discovery. But Telnet is a great shorthand if you just want to connect to a port and see what happens and look at something. You can use Telnet to send an email. You can connect to an SMTP server on the SMTP port from Telnet, and you can start passing commands just from the keyboard directly into SNMP and see how it reacts. And based on that, you can do some reconnaissance, but B, you could attack the server by sending certain commands, or you can even automate that with batch files and scripting languages like bash scripting and so forth. So lots of things that you can use Telnet for as an attacker. I don't think I have any labs where you do this, where you use Telnet, but I can record a video if you're interested and show you some different ways that you can use Telnet for attacks. The two main protocols that we have available with IP is IPv4 and IPv6. I'll talk about IPv4 first, which is the current version of IP, which was developed all the way back in 1981, along with TCP, which was also developed in 1981. The number of available IP addresses is limited to only 4.3 billion, which sounds like a lot, but that's fewer than the number of people on our planet. And if you think about it, every device on the internet now has to have an IP address. So it's certainly become a major vulnerability. Not a vulnerability in the sense of an attack or IT security, but if eventually we run out of IP addresses, then the internet won't work, which is a problem. And it has many security weaknesses as well. IPv6, which is the newer version, the next generation protocol, it addresses many of the weaknesses with IP version 4. Mainly, we have a lot of addresses available to us. We no longer have that 4.3 billion limited scope of, or limited number of IP addresses. Now we have almost unlimited IP addresses, and I can't imagine that we're going to need all the IP addresses available to us with IPv6. Although now that I said that, in like 2 years, somebody's going to listen to this video and think, oh wow, he was wrong about that. But I guess you never know. But there are a tremendous number of IP addresses available on IPv6. The other thing that IPv6 brings us that we care about in IT security, that's important for us in IT security, is cryptography, encryption. So encryption is baked into IPv6. So it includes encryption standards. One thing I want to mention, though, is encryption technologies change, and I foresee that in the next 5 to 10 years, we're going to see a major shift in encryption technologies because of things like quantum computing, and just the computing power is getting so much more powerful that a lot of the encryption that we do today may not be as effective in the future, and protocols are going to have to be developed. It's sort of a cat and mouse game, but protocols will have to be developed to handle that. So, I predicted IPv6, may not see as much usefulness as people thought because of that issue. And the other thing is IPv6. I'm sure that most of you probably are aware of IPv6, but I'm willing to bet that if there are if 100 people watch this video, gosh, that would be crazy. Nobody ever watches my videos. But let's say 100 people watch this video. Out of 100 of you, probably 2 of you use IPv6 in your network at your place of business. The rest of you probably only use IPv4. So things like natting really alleviated the need for us to move to IPv4 on our internal networks. And IPv4 is just easier to manage. Network administrators understand it, so they're reluctant to switch to anything else. So it's one of those things that we haven't really seen a lot of people migrating to IPv6, at least on their internal networks. But we do see IPv6 very frequently implemented on the internet itself. But you do have to, in order to use IPv6, you have to support it, obviously. And some internet properties are only now supporting IPv6. But most of the firewalls and routers on the market can support that. So even if our internal network is only IPv4, we can support the IPv6 networks out on the wider internet. So some of the enhanced security features, again, it's cryptography, so it adds encryption, the authentication headers, which you'll learn more about with your VPNs. So now we can natively create tunnels with IPv6, which is definitely a major enhancement. So in the next video, I'm going to stop this video here, and in the next video, I'm going to talk about some network administration principles. So basically some network administration best practices we can use for IT security and network security.